Practice problem says TXY and XY diagrams are plotted below for the acetone methanol system at 1.5 atmospheres with the activity coefficients described by the Margulies activity model. And there are some parameters here that are set arbitrarily. So this is very similar to problem 4 from homework number 1. So if you're curious about how I did this, it's the same procedure that I used back then. Let's just go through the questions. A 40% acetone, 60% methanol mixture is brought to 64 C and 1.5 atmospheres. What are the compositions of the vapor and liquid phases? Pause the video here and see if you can do this. You have the ability right now to solve this problem. It doesn't require any special ability. The only weird thing is that the TXY diagram looks a little bit stranger than it typically does. So finding what my initial composition is, I want to go to 40% acetone, and by default then 60% is methanol. And we don't know what the original temperature is. I guess it doesn't really matter. It could be vapor or liquid. Remember, for a TXY, vapor is on the top, liquid is on the bottom, and anything in between is in the two-phase region. 64C and the entire TXY diagram is for 1.5 atmospheres, so it's good to double check. But finding where the intersection is, 64C is right in the middle there. And to figure out what the vapor and liquid compositions are, I draw myself a horizontal tie line, and I trace that down to read what the mole fractions are. So in my vapor phase, for my vapor phase, I want to remember look off of the dew point line, and that's the light blue line. And that one's super easy. It's 50% acetone, which means it's 50% methanol as well. 50% A, 50% M. The liquid is a little bit more involved. The liquid, it looks like I've got, let's say 31% acetone, which means that the remaining 69% is methanol. All right, number 1 wasn't too bad. Number 2 says an 87% acetone, 13% methanol mixture is brought to 64 C and 1.5 atmospheres. Interestingly, these are the same temperature and pressure. So your first instinct might be, well, for Gibbs phase rule, remember, is 2 plus 2 minus 2 in this case, which means if I set 2 of the intensive variables, and I've set pressure and temperature here, then that sets my mole fractions, right? And that is right in some sense. However, it's not the same value. So you can't just say if my pressure and temperature are the same, then my mole fractions are the same. You have to use the diagram, and the presence of this azeotrope messes it up a little bit. Another way I like to think of it is like these dew point lines and the bubble point lines are not functions of y, because there are 2 values for them. So in other words, 87% acetone is over there, 13% methanol. And if I go up to 64 degrees, well, now I'm in the other regime of the graph, as it were. So I have to read my compositions by drawing a tie line over on this side, and then drawing my lines down to see what the compositions are. So in this case, remember, my vapor is still off of the dew point line, which is the light blue line, and the liquid is off of the bubble point line, which is the dark blue line. So it looks like my vapor is, let's see, 85% acetone, and that means the other 15% is methanol. And my liquid mole fractions are 94% acetone and 6% methanol. Something else interesting has happened here. I want you to pause the video and see if you could think about what I'm about to say here. And that is that if you ask the question of which one is more volatile, they look like they have flipped. So in other words, in scenario 1, my original mixture is 40% acetone. And after I do the separation, my vapor is 50% acetone and my liquid is 31% acetone. So it means that acetone is enriched in the vapor phase, and that's typically what we assign to the more volatile. So in scenario 1, we might say that acetone is more volatile. However, in scenario 2, 87% acetone, now my acetone is enriched in the liquid phase. and depleted in the vapor phase. And that leads me to believe that my other component, methanol, if I look at methanol, 13% is in the original mixture. Now 15% means methanol is more enriched in the vapor phase. So methanol has now somehow become my more volatile. So that's the first challenge that we'll have to deal with in azeotropes, is that it doesn't make any sense to say which one is the more volatile component anymore, because it depends on what your composition is. So bear with me, we'll get through this after some initial confusion. Next question is a liquid mixture of 67% acetone. Right there, 33% methanol is boiled, and we boil it by bringing it to the boiling point. What is the composition of the vapor? I've already gone through this a little bit, but the composition of the vapor will be 67% acetone, 33% methanol. Now, all of a sudden, the basis of separation that we've been using, which is that when you boil it, the vapor is a different composition than the liquid, that is no longer true. So that's the second thing that we'll have to deal with azeotropes. But I want to mention that it's not that you may think like you can never separate an azeotropic mixture, but that's not true, because in questions 1 and 2, we were still able to separate it so long as our composition was not near the azeotrope. Right, so as long as my composition is not near 67% acetone in the beginning, I can still get decent enough separation. But that has a limit to it, as we'll see in the second part of the problem a little bit later. What is the composition and boiling point of the azeotrope? Well, the composition is the same, 67% acetone, 33% methanol. So there's like it's an azeotropic mixture, but the azeotrope is only at one point, and that's where the liquid and the vapor mole fractions are equal. Is the azeotrope a maximum or minimum boiling azeotrope? I haven't mentioned this, and this is another curious thing that happens with azeotropes. But if I go back to what the TXY diagram was for an ideal or a zeotropic mixture, the bubble point and the dew point, in other words, where these curves were always in between the pure component boiling points. So if I look, that's not true anymore here. The pure component boiling point for methanol, remember, so methanol is 0% acetone, 100% methanol, is 75 degrees. So boiling point for methanol is 75 degrees C. The boiling point for acetone is 68 C. Curiously, so we brought this mixture to 64 C, which is below the boiling points for both pure components, and yet we still have equilibrium forming. So that's a little bit of a weird thing here. The boiling point of the azeotrope is 62 degrees C. So the question of whether it's a minimum or maximum boiling azeotrope, most azeotropes that you see are going to be minimum. There are a few examples of maximum. I'd say just a majority are minimum. It's not like an overwhelming majority or anything like that. It's a minimum boiling point azeotrope because the boiling point of the azeotrope is between, or they're less than, sorry, is less than pure component boiling points. And if I had a maximum boiling azeotrope, the TXY diagram would look something like this. So the boiling point of the azeotrope would be above, so this is the boiling point of the azeotrope, above the pure component boiling points. Which component is more volatile? We covered that already. The answer is it depends. It depends on what the composition of your original mixture is. If you have a lot of acetone, then methanol is more volatile. If you have a little bit less acetone, then acetone is more volatile. So that was some introductory questions. Next video, we'll get into this problem below.